the point of using capacitors is so that we can store charge or store energy. And so what we're going to do first is look at the energy and then talk about if we have more capacitors, do we get more charge, more energy? So first to the energy. Okay, so our expression for capacitors is that we have Q, the charge stored, goes as the capacitance times the voltage. So if we're going to find the energy stored, one way we can do it is to look at the work to charge a capacitor. And so as we add more and more charge, we would be adding up the additional amount of work to add more and more charges. So this would look like then our work is related to our potential, or our energy, if you like, is related to our voltage, our electrostatic potential. And so if we have our V, and then we keep adding little charges, then as we get our total charge, then that will allow us to find our work. Now this voltage does depend on the amount of charge. If we just look at this equation, we can see if we rewrite it, it would say voltage is equal to our charge over C, and I'm making this small q to kind of differentiate it from our total charge. If I plug this in here, then I can see that I've got an integral from 0 to Q total of Q over C dq. And now this C, that's dependent on the geometry of our capacitor. Remember, it depends on the area and the spacing. So that's a constant that we can pull out. And so this work to charge a capacitor, or another way to look at that would be the energy that's stored in the capacitor, is equal to 1 over C dq times Q, 0 to Q total. And so this becomes 1 over C 1/2 Q squared, right? This is our power rule. We increase the power, evaluated from Q total to 0, which is just 1/2 Q total squared over C. If I want, I can now plug in my total voltage, the voltage that I used of the battery to charge this up, and that would be in place of this Q, one of the Q's, I could say that would be a voltage times C if we like, or I could say that 1 Q over C is a voltage. So there are a number of different ways you can write this. Q times V 1/2 Q squared over C, or you could get it in terms of C and the voltage. But this tells you then the energy that's stored. So the energy stored in a capacitor, typically we see it like this, as 1/2 charge, the total charge that's stored, and the voltage. And again, if you want to substitute in here, you can get any of the other versions of the energy stored. Okay, so that says if we want to store more energy, we obviously want to store more charge. And so we can look at, well, instead of one capacitor, what if we use multiple capacitors? Okay, so we have charge, we have U for the energy stored. That's the notation that your book uses, but you can just translate that in your head if you want energy stored. But this is going to have still units of joules because charge is coulombs and volts is joule per coulomb. So all the units work. Okay, so we want to store more charge. One way to do that is to, of course, build a bigger capacitor. But if we have only a certain size capacitor available, there are really two ways to think about providing more charge. Two ways, and then we can combine those ways. So one is we take a battery, power supply, and we hook it up to two capacitors, and this is called capacitors that are in parallel. So there's C1, and they don't have to have the same capacitance. So C1 and C2, there's a voltage difference between these two plates. So I'll write this as a V. Often to be strictly correct, you really want a delta V, but this is what's used a lot. So I'm going to just use that. So this is called a parallel configuration. And then a series is when they're in line. So we can have series, where we have like this, capacitor 1 and capacitor 2. Again, they don't have to be the same size, and then a voltage. Okay, so what we're going to do is start over here with the parallel case, and then we'll look at the series case. We'll sort of compare them along the way. The first thing to note is in a parallel case, you can really see it as each capacitor has its own connection to the battery, right? This capacitor has the connection that looks like this to the battery. But the other capacitor, this one that's way out here, you could think about moving it to the other side if you want. Each plate, this side, sees directly this side of the battery, and this side sees directly the positive side of the battery. So they have their own connections. So each of these capacitors has the same voltage. If I measure the voltage across here, that's the same as across here, and this voltage is the same as across here. So they both have the same voltage, delta V. Okay? But that means they're likely to have different Q values because they have different capacitance, right? So if so this I'm going to call Q1 and this I'm going to call Q2. And what I'm going to realize is that Q1 is equal to C1 times its voltage, but it's the original battery voltage, and Q2 is equal to C2 times the voltage, and the voltage is the same. And so we can store charge here and here, and the total charge that we store, Q total, is just going to be Q1 plus Q2, and I can substitute in for that, so that would be C1V plus C2V, or my total charge is going to be C1 plus C2 times V, and so this is going to be basically my total capacitance. So for parallel situation, so I'll write this up here, for parallel, when I add them in parallel, my equivalent capacitance, my net capacitance, is just going to be C1 plus C2 plus C3, however many of them I have. If I just have a big string, I can keep adding more and more capacitors to store more and more charge, and thus more and more energy. Now in the series case, this voltage is really across this. Right, this point is connected here, and this point is connected here. So these are splitting the voltage. The voltage across 1 plus the voltage across 2 equals this total voltage. Voltage is equal to 1 plus 2. In other words, if this is 9 volts, we might have 3 volts across here and 6 volts across here. It just depends. What's the same, however, is the following. So as I connect these up, notice I get some positive charges, and then I would get some negative charges. But if I have 4, whatever units, negative charges on the bottom of this plate, I have to have 4 on the top of this plate right here, because this wire, I can't just pile up extra charges in the wire. They're going to separate from each other. I can't say, let me have 3 charges there and put 1 here. That doesn't work, because this charge is like, yeah, I don't want to be, that doesn't work for me, okay? And so the charges are sitting here. You know, these 4 charges would like to be with these, but they're also attracted down here because of the battery that we've got set up, so that as this side charges and this side charges, they charge so that we have equal amount of charge on either plate. We can't have an unequal charge. And so in this case, the voltage adds together and the Q is the same on both plates, which means the Q is going to be limited by the plate that can hold the most for that voltage. So if we say Q is the same, then we can have Q for the first one is going to be C1 V1, and Q for the second one is C2 V2. And if we rewrite these and substitute in right in here, this gives me my total voltage is equal to Q over C1. So I'm plugging in, rewriting this equation, plugging it in for V1 plus Q over C2. And that tells me, in fact, that V is equal to, factoring out the Q, 1 over C1 plus 1 over C2. Or if I want to put this in the form Q equals CV, then I would say Q is equal to, I got to divide by this whole thing. So 1 plus C1, 1 over C1 plus 1 over C2, all to the negative 1 times V. And so this quantity right down here is my equivalent capacitance. Okay, so for series, my C equivalent is 1 over C1 plus 1 over C2 plus 1 over C3 and so on, all raised to the minus 1. And so what that tells you is that if you put some numbers in here, if we just put 1 and 1 in here, for example, and say we don't have a C3, then that gives me a 1 over 1 plus 1 over 1 gives me 2, and then I take it to the minus 1, my equivalent capacitor is smaller. Okay, so this is a situation where my equivalent, my total capacitance is actually smaller. And you might say, well, that's a waste. Why would you ever do that? This makes sense. We can have more charge and more energy. The only time this makes sense is if your voltage here is so big your capacitor can't handle it, and that happens. So I had a laser that needed a lot of energy, right, to get it to laze, to create the nice, powerful laser beam that I needed. And so I had a power supply that I was trying to build up charge, but I had capacitors. The manufacturer had put in capacitors in parallel, but also they had some that were in series, so it would be like 2 in each of these, because the voltage each one had to hold was several thousand volts, and the capacitor just couldn't handle it. So we had a couple of capacitors in series, so we would divide up that 1,000 volts to say be 500 volts if I had 2, or 333 volts if I had 3 of them, and so forth. So that's when you would use something like this. But I want you to get used to this language of recognizing something is parallel, and that's when their top and bottom sides are connected, or in series, which is when you think of one plate next to the negative plate of one next connected to the positive plate of the other. Okay, because we're going to use this language again going forward.